This lesson deals with diode logic circuits. You can find these notes in the ECE302 ebook in Chapter 2 starting on page 70. Logic circuits have inputs that are two-leveled. Suppose I define a logical 1 or a high level as a voltage that's between 2.5 volts and 5 volts, and a low level or logic 0 between 0 volts and 2.5 volts. Suppose I have this circuit here with 3 non-ideal diodes and a resistor and 3 possible inputs. Our inputs will just be two levels, either in this case 0 and 5, and then we'll see what the output is and see where it falls in our inequalities. Given 3 inputs that can be either low voltage or high voltage, in this case 0 volts and 5 volts, there's 8 possible combinations. Let me pick one of these and see if we can kind of figure out how the circuit's working, and then we can project the other ones. I'm going to hook up 5 volts here, 5 volts here, and 0 volts here. This is the case here of 0, 5, 5. If I have 5 volts here, current would want to flow in this direction, so I'm going to guess that diode B is on. And current, of course, can't come back this way or can't go back this way. Likewise for diode C, I could see current could flow this way, but it can't flow this way or this way. I guess that diode C is also on. Since I have 0 volts here, I don't have any voltage to push a current in this direction. I can't get currents to come back this way, so I'm going to guess that probably diode A is off. Let's model these diodes with an ideal diode and a battery, and then we'll take our guesses and see if they're correct. So I replace diode A with an ideal diode and a battery of 0.7, a short in 0.7, and a short in 0.7. I'm going to solve for the voltage across the diode and the current through the diode to verify the guesses. We can solve for the output voltage because here I've got 2 voltages and then a voltage back to ground. So the rise in voltage would equal the drop. So I got the rise in voltage would equal minus 0.7 plus 5, or 4.3. What's the voltage across this diode? Well, this node voltage is 0, and this node voltage is 0.7 plus 4.3. So we're going to subtract 5 volts, we get a minus 5. So that checks that that diode is off. The current in this diode and the current in this diode flow into the resistor. And the current in the resistor is the voltage of 4.3 divided by R. Technically, these two diodes are soldered in parallel. Physically soldered here, but with these two voltages being equal, it's as if they were soldered with one 5-volt battery. If I assume that both diodes are identical, then they have the same voltage across it and would therefore have the same current. Write down the sum of currents is actually twice, say the first one. Now I can solve for the current in the diode. It's going to be 4.3 divided by R and then divided by 2. And then it's greater than or equal to 0, so our guess checks. One point here is if the diodes are not identical, this is still true. We literally have them tied in parallel. But if one's a little bit different than the other, then for the same voltage, you'll get a slightly different current. In IC design, we call that a current hog, because that one takes more current than the other ones. That can cause all kinds of problems, as you can imagine. We also generalize our results and say that whenever one input is high, we'll have that diode on, and that'll force the output to be high. In this case, 4.3 is between 2.5 and 5 volts. Let's fill in our voltage table. We started with 0.55. We found that the output was 4.3, but really, if we just have one input that's 5 volts, that'll forward bias that diode and force the output to be 1 diode drop less than the input. That's true here, it's true here, it's true here, true here, true here, and true here. The one case we didn't take a look at is what happens if all the inputs are 0. Let's back up and look at that on the previous page. If this was 0 and this was 0, then we wouldn't have any source of power to forward bias the diodes. All the diodes would be off, because all we've got are passive circuit elements, nothing able to generate energy. So the output voltage would just be equal to 0. And that's our first entry in this table. For those that had a logic circuit course like ECE302, we can write this in what's called a logic table, where voltage is less than 2.5 volts would make that a logical 0, and those that are greater than 2.5 would make that logical 1. What I've got here is that when all the inputs are 0, the output is 0, and when any one of the inputs is 1, the output's equal to 1. There's a Boolean expression for this in logic circuits. You don't need to know that for this course, but it would be A or B or C. Let me do an example maybe to show you where you might use something like this. Suppose I have a battery, and I have 3 switches in parallel. And a light bulb. Symbol for a light bulb is a circle with rays coming out of it. Suppose that these switches are what are called normally closed switches. That is, when you don't do anything to the switch, these 2 points are shorted together. So if I take an action, then I open the switch. Suppose these are connected in doors like your refrigerator. When you close the door, the light goes off, and when you open the door, the light comes on. If you were to close the door, you push this switch open, and no current would flow. But now we've got 3 of those. So maybe you got a refrigerator with 3 doors on it. Might look kind of weird, but there you go. Whenever all the doors are closed, these would then be open, the light would be off. But if any one door is open, or 2 doors are open, or all 3 doors are open, the light will come on. Our last circuit was called an OR circuit because when one or more of the inputs is high, the output's high. Take a look at what's called an AND gate. I'll take 3 diodes again, although actually you can have as many as you want. It just extends the table. 1 resistor and 1 battery. And I'm going to hook up one case, and we'll see if we can guess what the rest of them are going to do. Suppose they make this 0 volts, and this 0 volts, and this one 5 volts. What's going to happen? Well, if I have 5 volts here and 0 volts here, the voltage across this resistor and diode is 5 volts, so current's going to want to flow in this direction. I'm going to guess that diode A is on. For diode B, though, I have 5 volts here and I have 5 volts here. 5 volts minus 5 volts gives me 0 volts across this series combination. And if current were flowing, I'd have more than that. That probably is off. And then for case C, I've got a voltage here of 5 volts and 0, so across this resistor and this diode, I have a total of 5 volts. Most likely current's going to flow. We'll model a non-ideal diode with an ideal diode and a battery. In this first case, it's a short. In the third case, it's a short. And in the second case, it's an open. Let's even figure out the output voltage. Since I have a short and a battery, I just go around the loop this way. So the rise in voltage would equal 0.7 plus 0, so the output's 0.7. Let's use that to find the voltage across this ideal diode. This node voltage is minus 0.7 plus 0.7. We're going to subtract this node voltage of 5. These cancel, I get minus 5. So you have diodes off. The current that's in here is going to be equal to the current in here and the current that's in here. And the current in this resistor is the voltage across it, which is going to be 5 volts minus 0.7 or 4.3 divided by R. And then this current is the same as this current, so the current in the diode is going to be half of that. This is a positive number if the diodes are identical. And if they're slightly mismatched, it would also still be greater than 0 for each diode, just that one may have a little bit more than the other one. Or guess checks. Can we extend this to the rest of the cases? Well, whenever one input is low, the output will be low. Now, the one case we didn't take a look at is what happens if all 3 of these are high. If this was 5 volts, this was 5 volts, and this was 5 volts, then the difference between here and here would again be 0 volts, and no current would flow. And this node voltage is going to be the same as the battery. And that would be logical 1. So here's our table. We did the case of 0, 5, 0, found that the output was low. But whenever I have 1 or more zeros hooked up to the input, current flows through that diode. So this would also give me a low, this would 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 give me a low, and this would give me a low. The case that's quite different is the one where all inputs are 5, and now all the diodes are off. That's our voltage table. Our logic table would be 0 volts corresponds to logic 0, and 5 volts corresponds to logic 1. And here's a voltage between 0 and 2.5, so that's logical 0. And then here's 5 volts, which would be logical 1. There is a thing called a Boolean expression for this, and it's called the AND function, where I have A and B and C. What that means is that if the 3 inputs, A, B, and C, are logical 1, then the output's logical 1. But if 1 or more are 0, then the output is 0. Let me give an example where we might use something like this. Let's take a battery again. And I have 3 switches now, but they're in series. With a light bulb. These are called normally open switches. When you press the switch, it'll close it. Suppose now that when a door closes, we close the switch. One door closes, the light doesn't light. I would have to have all 3 doors closed before I'd light the light. Maybe use this on an airplane. If the doors in the airplane are not closed, don't start the engine. And these are diode logic circuits.